The theory of everything in physics refers to the search for a single, unified framework that explains all fundamental forces, particles, and interactions in the universe. So far, we've discovered powerful laws and equations that describe different aspects of reality: the motion of planets, the behavior of atoms, and even the origin of the universe. However, each of these laws applies only to a specific part of reality. For example, general relativity explains gravity with remarkable accuracy, while quantum mechanics captures the bizarre behavior of particles at the smallest scales. But when we try to apply both theories together, such as in the center of a black hole or the first instant after the Big Bang, the math breaks down. The idea behind the theory of everything is to find one equation that unifies all of physics, from the curvature of space-time to the structure of matter. Despite decades of effort, scientists have yet to discover this unifying principle. Theoretical models like string theory, loop quantum gravity, and grand unification theories offer potential answers, but none have been experimentally confirmed. This raises a deeper question. Is there truly a single elegant principle behind all of nature, or is the universe inherently fragmented? Ultimately, the theory of everything isn't just about merging physics. It's about uncovering whether reality follows a hidden, universal code or whether the final piece of the puzzle simply doesn't exist. One lingering mystery is why the universe appears to be missing antimatter. Galaxies, stars, and planets all drift through space. But curiously, they seem to be moving toward a single mysterious region. This powerful pull comes from a place known as the Great Attractor, a gravitational anomaly that has puzzled scientists for decades. Located within the Lania Chaos supercluster, the vast region of space that also contains our Milky Way, the Great Attractor appears to be drawing galaxies toward it at incredible speeds, over 2 million kilometers per hour. Yet, despite its enormous influence, its true nature remains hidden. The main reason we can't see it clearly is because it's located behind what's called the zone of avoidance, an area of space obscured by the dense stars, dust, and gas in the plane of our own galaxy. We can detect the gravitational effects, but we can't directly observe the source. What exactly is causing this immense pull? Some scientists believe it could be a supermassive black hole nestled at the heart of a colossal galaxy cluster. Others suggest it might be an enormous collection of galaxies packed so densely that their combined gravity is warping space-time itself. But none of these ideas have been confirmed. The mystery of the Great Attractor raises deeper questions. Is it simply a massive object we haven't seen yet? Or could it represent something even stranger? Something that challenges our fundamental understanding of the cosmos? As astronomers continue to investigate, the Great Attractor remains one of the most compelling and unresolved enigmas in modern physics. A reminder that much of the universe is still beyond our grasp, and that other powerful, unseen forces may be shaping the cosmos in ways we have yet to uncover. The arrow of time paradox explores one of the most intriguing mysteries in physics: why time seems to flow in a single direction, from the past toward the future. We naturally perceive this flow, remembering the past, but never the future. We see irreversible events like a glass shattering, but never witness it reforming on its own. This one-way movement of time feels intuitive, yet it raises a fundamental question: why does time only appear to move forward? Interestingly, the fundamental laws of physics, such as those governing motion and gravity, are time-symmetric. They work equally well whether time moves forward or backward. In theory, nothing in these laws prevents time from running in reverse. So why don't we ever experience time flowing backward? The key to this puzzle lies in the concept of entropy, which is a measure of disorder. As time progresses, systems tend to move from order to disorder. Ice melts, buildings decay, and messy rooms don't clean themselves. This tendency for entropy to increase gives time its apparent direction: forward. In other words, rising disorder creates what we perceive as the arrow of time. But here's where the paradox deepens. Although increasing entropy explains our perception of time's direction, it doesn't explain why time is linked to entropy in the first place. Why should the progression of disorder determine the flow of time? The arrow of time paradox continues to puzzle scientists. It's not just a question of physics, but one that touches on the very nature of reality and human experience. Could the flow of time be far more mysterious than it appears? For now, the answer remains unknown, hinting at deeper truths yet to be uncovered about the universe. Black holes are known for their immense gravity, pulling in everything around them, even light. But what if there were objects that did the exact opposite? Enter the fascinating and mysterious concept of white holes. White holes are theoretical constructs in physics, predicted by the same equations of general relativity that describe black holes. While black holes have event horizons, boundaries beyond which nothing can escape, white holes are said to have a boundary that nothing can enter. Instead of consuming matter and energy, they would expel it, functioning like a kind of cosmic fountain. The idea of white holes emerges naturally from the mathematics of black holes. If you reverse the flow of time in the equations describing a black hole, you get the conditions for a white hole. In this reverse scenario, instead of pulling everything inward like a black hole, a white hole would force everything outward. But this leads to a paradox. How can matter and light emerge from a region that, according to the laws of physics, should be completely sealed off? While black holes have been directly observed in space, no white hole has ever been detected. This leaves scientists wondering whether white holes are actual objects in the universe or just mathematical artifacts with no real counterpart. Some theories go even further, suggesting white holes could be connected to wormholes, possibly linking distant parts of the universe or even acting as gateways to other universes. In some speculative models, a white hole might be the exit point for matter that falls into a black hole, re-emerging in a completely different region of space-time. Yet without any direct observational evidence, white holes remain one of physics' most compelling mysteries, an idea that stretches the limits of our understanding and imagination. Do they exist somewhere in the farthest reaches of space, or are they simply elegant solutions written in the language of mathematics? For now, the answer remains unknown. In the vast depths of space, there may exist bizarre entities that challenge everything we think we know about the universe. These are known as exotic vacuum objects, and they could be more mysterious and possibly more dangerous than anything we've ever encountered. These theoretical objects are believed to form in the vacuum of space, which, contrary to what we once thought, isn't truly empty. Instead, space is filled with fluctuating quantum energy. Under certain extreme conditions, this energy could give rise to strange and powerful states of matter, what we call exotic vacuum objects. What makes them so unsettling is that we don't fully understand them, and it's unclear whether they even exist. The concept is rooted in a theory known as vacuum decay, which suggests that the vacuum of space might not be in its most stable form. Instead, it could have multiple phases or states. If triggered, a shift from one phase to another could create incredibly dense and unstable objects with potentially destructive effects. In some theoretical models, exotic vacuum objects behave like cosmic bubbles of strange matter, capable of growing larger and spreading outward, altering the very nature of space around them. Imagine an object that doesn't just defy the laws of physics, but rewrites them. A force like a black hole, yet not bound by the same rules, capable of consuming everything in its path. The true mystery lies not just in what these objects might be, but in how they would behave if they actually formed. Would they collapse into black holes? Would they vanish entirely? Or could they be drifting through the far reaches of space, unseen and dormant, waiting for the right conditions to activate? Although still hypothetical, exotic vacuum objects push the boundaries of our understanding. They compel us to ask a deeper question. Is space truly empty, or are hidden forces at play, shaping the universe in ways we can't yet comprehend? Something strange is unfolding in the fabric of space, something invisible yet incredibly powerful. Scientists refer to it as phantom energy, and it may hold the key to one of the universe's greatest mysteries. We've long known that the universe is expanding, but the surprising discovery is that this expansion isn't slowing down, it's actually speeding up. This unexpected acceleration is attributed to dark energy, a mysterious force believed to make up about 70% of the universe. But phantom energy goes even further. Phantom energy is considered an extreme form of dark energy, one that could accelerate the universe's expansion at an ever-increasing rate. This leads to a haunting possibility. If the acceleration continues to intensify, entire galaxies, stars, and even atoms could eventually be torn apart. It would be as though the very fabric of space is being pulled to pieces, and phantom energy might be the driver of this cosmic unraveling. Scientists are still trying to fully grasp how phantom energy works. It may be related to Einstein's concept of the cosmological constant, a term he introduced in his equations of general relativity. However, phantom energy suggests a much more dramatic future, one where the acceleration of the universe doesn't stabilize but instead continues to increase forever. This could lead to a doomsday scenario known as the Big Rip, in which the entire universe is eventually torn apart at the seams. Whether phantom energy is a temporary phenomenon or the universe's final fate remains unknown. As researchers study dark energy and its more extreme cousin, phantom energy, they are uncovering a powerful hidden force, one that could reshape everything we believe about the destiny of the cosmos. At the very beginning of time, the universe underwent a dramatic event known as cosmic inflation, a rapid expansion that caused it to grow from subatomic scales to an enormous size in a fraction of a second. But what if that inflation never truly ended? What if, instead of stabilizing, it continued indefinitely? This leads to the fascinating and unsettling idea known as the eternal inflation paradox. According to the theory of eternal inflation, cosmic inflation didn't stop everywhere at once. Instead, while some regions slowed down and formed what we now recognize as our universe, other areas kept expanding. This ongoing inflation causes bubbles of space-time to form endlessly, each potentially becoming a separate universe with its own unique laws of physics, constants, and cosmic structures. In this view, our universe is just one bubble in a vast, ever-growing multiverse, a network of countless universes expanding at different rates. But this raises a major paradox. If inflation never stops and new universes are constantly being born, how can we ever fully understand the nature of reality? The infinite nature of this process challenges our ability to define or measure the universe as a whole. Eternal inflation also poses deeper questions. What happens to the fundamental laws of physics in this multiverse? Are gravity, matter, and energy consistent across all these bubble universes? Or could they vary wildly? If so, it suggests that our understanding of the cosmos might only apply locally, not universally. The eternal inflation paradox is more than just a theoretical curiosity. It pushes us to reconsider the very foundations of how the universe began, what it is, and where it's headed. As scientists delve deeper into this mind-bending concept, they may reveal a reality far more complex and far more infinite than anything we've previously imagined. Scale relativity. Everything in the universe is connected through scale, from the tiniest particles within atoms to the largest galaxies spread across space. The laws of physics seem to behave differently depending on the scale at which we observe them. But what if our very understanding of space, time, and reality itself also shifts with scale? That's the intriguing idea behind scale relativity. This concept asks a fundamental question. Do the same physical laws apply regardless of size? In our daily experience, the world follows clear rules. Gravity pulls objects down, and motion is predictable. Yet, at the quantum level, those rules begin to unravel. Particles behave unpredictably, often existing in multiple states at once. Scale relativity explores what happens when we examine all levels of existence, from subatomic particles and atoms to the vast structure of the cosmos. Just as Einstein's theory of relativity revealed that space and time are flexible and shaped by gravity on large scales, scale relativity proposes that similar shifts might occur on the smallest scales. It suggests that the same fundamental principles might govern both the massive and the minuscule, though their effects may differ. This implies that the laws of physics may not be universally fixed. They could vary with scale, hinting at a more dynamic and unpredictable reality. One of the most compelling aspects of scale relativity is its potential to link quantum mechanics with general relativity, two foundational theories of physics that have never been fully unified. Could this idea be the missing piece that connects our understanding of the universe at every scale, from particles to galaxies? The concept challenges scientists to rethink how physical laws operate across all levels, possibly holding the key to unlocking the true nature of reality. When most people think of black holes, they picture a point of no return, the event horizon, where nothing, not even light, can escape. But what if crossing that boundary wasn't a quiet one-way passage? What if something far more violent awaited on the other side? This is the unsettling idea behind the black hole firewall paradox. According to Einstein's theory of general relativity, passing through a black hole's event horizon would feel completely normal at first. From your perspective, it would be like crossing an invisible line with no immediate effects, until you're crushed by the singularity at the center. But things get far stranger when quantum mechanics comes into play. Quantum theory insists that information cannot be destroyed. However, if something falls into a black hole and disappears forever, as general relativity suggests, that information seems to be lost, creating a major conflict between two of physics' most important theories. To address this, some physicists have proposed a radical idea. Rather than being smooth and uneventful, the event horizon may actually be surrounded by a firewall, a searing wall of high-energy particles that would incinerate anything trying to enter. This concept of a black hole firewall challenges our current understanding of space, time, gravity, and information. If firewalls exist, they break the rules of relativity by making the event horizon a deadly boundary. If they don't exist, we're left with a deep paradox. How can both general relativity and quantum mechanics be right if they offer contradictory outcomes? At the core of the firewall debate is the tension between how the universe behaves on the largest scales, relativity, and the smallest scales, quantum mechanics. The paradox remains unsolved and is one of the biggest obstacles in the quest to find a unified theory of physics. What really happens when something crosses a black hole's event horizon? The answer may hold the key to understanding the true nature of reality itself. The measurement problem, a mystery at the heart of reality. One of the most perplexing mysteries in modern physics is known as the measurement problem, a question that has baffled scientists for decades. At its core, it asks, how does the fuzzy, probabilistic world of quantum particles transform into the clear, predictable reality we experience? In the quantum realm, particles like electrons and photons don't have fixed positions or velocities. Instead, they exist in a state of superposition, a range of probabilities where they can be in multiple places or states at once. But something strange happens when we observe or measure them. The moment we measure a particle, it chooses a single state. This is known as wave function collapse. So what's the mystery? Why does observation itself seem to change reality? Before measurement, a particle behaves like a cloud of possibilities. After measurement, it becomes a single, definite thing. But how? And why? Does simply observing it cause such a drastic shift? This paradox lies at the heart of quantum mechanics. On one hand, the theory works brilliantly. Its predictions are extraordinarily accurate. On the other hand, it offers no clear explanation for why observation appears to force a decision upon nature. This raises even deeper questions. Does reality exist in a definite state before we observe it? Does our act of observing actually create the outcome we see? Is consciousness involved somehow? Some scientists speculate that consciousness might influence this process, while others believe there may be hidden laws of nature we haven't yet discovered. Though abstract, the measurement problem sits at the foundation of our understanding of the universe. It forces us to reconsider what reality truly means, and it may one day lead us to uncover the deeper truths behind the cosmos. Zero-point energy exploitation. Imagine harnessing an invisible, ever-present energy source that surrounds us, an infinite reservoir of untapped power with the potential to revolutionize civilization. This is the intriguing promise of zero-point energy, a mysterious quantum phenomenon found even in the vacuum of space. According to quantum mechanics, space is never truly empty. It's alive with fleeting particle fluctuations, suggesting that energy constantly pulses through the fabric of the universe. Theoretically limitless and clean, zero-point energy could one day eliminate energy scarcity by drawing power directly from the vacuum itself. However, despite decades of speculation and theoretical support, scientists have yet to discover a method to access or extract this energy. While some believe the key lies in mastering quantum fields and spacetime itself, practical attempts have yielded no breakthroughs so far. The quest to exploit zero-point energy continues to challenge the boundaries of physics, holding out the tantalizing possibility of a future powered by one of the universe's most elusive forces, if we can ever unlock its secrets. Theoretical magnetic monopoles. Picture a magnet with just one pole, either north or south, but not both. This is the concept of a magnetic monopole, a hypothetical particle that has fascinated scientists for over a century. Unlike everyday magnets, which always have two poles, monopoles would carry a single magnetic charge. The idea gained scientific traction in the 1930s when physicist Paul Dirac proposed that if such particles existed, they could explain why electric charge comes only in fixed, discrete amounts, a phenomenon known as charge quantization. Discovering monopoles could revolutionize our understanding of electromagnetism, one of nature's fundamental forces. Despite their theoretical importance, no one has ever directly observed a magnetic monopole. Some researchers believe they might exist under extreme conditions, perhaps deep within neutron stars or during high-energy particle collisions. The continued search for monopoles is one of modern physics' great pursuits. If found, they could unveil entirely new layers of reality and reshape how we understand the magnetic and electric forces that underpin the universe. What if the universe isn't just a vast collection of stars, planets, and galaxies, but something far more profound? What if it behaves like a giant neural network? This fascinating idea suggests that the cosmos might function similarly to how our brains handle information. A neural network, in simple terms, is a system of interconnected nodes, much like neurons in the brain, that process and transmit data. It's the foundation of how deep learning works in artificial intelligence. Now imagine the entire universe working in a similar way. Billions of galaxies acting like neurons in a colossal cosmic network, constantly interacting and exchanging information. This theory isn't about the universe looking like a brain. Instead, it explores the possibility that the universe functions like a brain, processing information through intricate patterns and connections between seemingly unrelated parts. Some physicists propose that everything, from quantum particles to the large-scale structure of the cosmos, might operate as part of a massive information processing system, much like how a neural network learns, adapts, and evolves. Could the universe itself be thinking, learning, evolving in ways we've yet to comprehend? Could the laws of physics, like gravity and electromagnetism, be similar to synapses, the connections that link this grand cosmic network together? Some even speculate that consciousness itself may emerge from this vast neural structure of the universe. While still highly speculative, this theory challenges us to view the universe not as a passive stage for life, but as an active, dynamic system, one that processes, adapts, and perhaps even understands. It invites a bold question. Is the universe not only evolving, but also becoming aware of itself? In the vast expanse of the cosmos, galaxies typically drift apart, moving away from one another as the universe expands. But what if some galaxies were being pulled in a completely unexpected direction? This strange and unexplained phenomenon is known as dark flow. Discovered in 2008, dark flow was observed when scientists noticed that certain galaxies, especially those near the edge of the observable universe, weren't just moving with the general cosmic expansion. Instead, they appeared to be drifting toward a specific region of space. This motion didn't align with any known patterns or forces, leaving scientists puzzled. What makes dark flow so intriguing is that it doesn't seem to be caused by familiar forces like gravity from nearby galaxies or clusters. Some researchers theorize that something enormous and hidden, possibly a massive structure far beyond the observable universe, is exerting a pull. This could be a gigantic cluster of galaxies or some unknown cosmic formation that we currently lack the means to detect. Even more fascinating is the possibility that dark flow hints at the existence of regions beyond the visible edge of our universe, areas that lie outside the limits of our instruments and understanding. If true, this raises profound questions. Could there be unseen forces, hidden galaxies, or even entire universes beyond our reach? dark flow challenges our current models of how the universe works on the largest scales. It suggests there may be much more out there than we can currently observe, something vast and mysterious that is subtly influencing the motion of galaxies. As scientists continue to investigate, dark flow remains a compelling clue that the cosmos may hold far more secrets than we ever imagined. Woodward Effect. The Woodward Effect is a mysterious and potentially groundbreaking concept that could transform our understanding of motion and propulsion. Proposed by physicist James Woodward, the idea suggests that it's possible to create thrust, movement without traditional fuel or exhaust, by manipulating mass through specific energy patterns. According to the theory, electromagnetic fields might cause tiny fluctuations in an object's mass, and if these fluctuations are controlled precisely, they could generate a propelling force. This would mean spacecraft could move without burning fuel or ejecting material, offering a radical alternative to current propulsion methods. Though some experiments have detected small forces that hint at the effect's existence, the evidence remains inconclusive and controversial, leaving scientists divided over whether it's a real phenomenon or just experimental noise. If proven true, the Woodward effect could eliminate the need for bulky fuel tanks in space missions and make interstellar travel more feasible. For now, it sits on the edge of science, an unconfirmed but thrilling possibility that could either rewrite the rules of physics or deepen the mystery of how the universe works. In the strange realm of quantum physics, one enduring mystery has puzzled scientists for decades: the mass gap problem. Picture a world where particles are either extremely light, like photons, or significantly heavy, like protons. Yet, curiously, there's a void in between. This unexplained gap, where stable particles should theoretically exist but don't, challenges our current understanding of matter's fundamental structure. According to the standard model of particle physics, particles and their interactions are well explained at both low and high mass scales. But in the middle, between the mass of a proton and particles like the Higgs boson, something is missing. This mass gap is more than just a mathematical oddity. It could hold the key to deeper truths about the universe. Some physicists propose that unknown particles, bound by powerful forces we have yet to fully observe, might exist within this gap. If discovered, these particles could offer insight into major mysteries such as dark matter or the forces that shaped the early universe. Far from being a mere technical detail, the mass gap represents a potential gateway to an entirely new layer of physical reality. Solving it could reshape how we understand everything, from subatomic particles to the very fabric of the cosmos. Quantized inertia theory. Quantized inertia is a bold and controversial idea that challenges some of the deepest assumptions in physics. Proposed by physicist Mike McCulloch in 2007, the theory offers a radical rethink of inertia, the resistance an object has to changes in motion. Traditionally, inertia is tied directly to mass, but McCulloch suggests it might instead be influenced by the energy fields that permeate space, such as vacuum fluctuations and dark energy. The theory becomes especially intriguing when applied to galactic rotation. Galaxies spin in ways that defy predictions made by standard gravity models, a mystery often explained by invoking dark matter. But quantized inertia offers a different answer. What if these strange motions result from a modified form of inertia on cosmic scales? Beyond explaining galactic dynamics, the theory hints at the possibility of new forms of propulsion by manipulating inertia at the quantum level, potentially transforming space travel. Though still outside mainstream acceptance, quantized inertia opens up profound questions about the very forces shaping our universe, pushing us to reconsider what we truly know about motion, mass, and energy. Hyperspace jump theories. What if we could traverse the immense distances of space in an instant, bypassing the slow crawl of conventional space travel? This is the essence of hyperspace jumps, a concept long rooted in science fiction but increasingly explored by theoretical physics. The idea suggests that, under certain conditions, space-time itself could be warped or manipulated to allow faster-than-light travel. Instead of journeying across vast interstellar distances, a spacecraft might access a higher-dimensional realm, a kind of cosmic shortcut, connecting distant regions of the universe. One major hypothesis involves wormholes, theoretical tunnels through space-time that could link two far-apart locations, such as Earth and a distant galaxy. Though captivating, wormholes remain purely speculative, and even if one were found, stabilizing it for travel remains unsolved. Another concept is the warp drive, which proposes bending space around a craft to move faster than light without violating physics. Yet, the energy required for such a system is currently beyond imagination. These ideas push the limits of our understanding and hint at the existence of hidden dimensions or forces embedded in the universe. Hyperspace travel remains an unsolved mystery, but it may hold the key to unlocking a radically new era of exploration, hidden within the very fabric of reality. Imagine a form of mass that doesn't obey the familiar rules of physics, one that repels instead of attracts, defies gravity, and moves in the opposite direction of an applied force. This is the bizarre concept of negative mass. In our known universe, mass is always positive. It pulls objects together through gravity, with larger masses exerting stronger attraction. But what if a type of mass existed that behaved in the exact opposite way? If you pushed an object with negative mass, it wouldn't move away. It would accelerate toward you, behaving as though your force were pulling it back. This flips our understanding of Newtonian motion on its head. While negative mass has never been directly observed, it's not ruled out by theory. Some exotic particles or extreme conditions might make it possible, and some scientists even speculate a connection to dark energy, the enigmatic force driving the universe's accelerating expansion. Whether negative mass is a real, hidden aspect of the cosmos or simply a mathematical anomaly, its existence would radically challenge our understanding of gravity, motion, and the fabric of the universe itself. If discovered, would we learn to control it? Or would it force us to completely rewrite the laws of physics?